introducing the nonlinear crystals into the cavity. That is called parametric amplifier. Parametric amplifier is one of the most interesting and well-characterized optical device in quantum optics. In this device, a pump photon of frequency to omega down converted into two highly correlated photons. So those nonlinear crystals can be divided into two depending on the frequency, down conversion frequency, degenerate parametric amplifier and non-degenerate parametric amplifier. Degenerate parametric amplifier is a phenomena in the nonlinear crystals. Where a pump mode of frequency omega down converted into two highly correlated of frequency to omega, that is degenerate parametric amplifiers. So parametric oscillator is a type of source of squeezed light, and the effect of this parametric amplifier is to increase the intracavity of the squeezing. The statement of the problem. Many pure workers focused on the quantum resistance property of dangerous reliable lasers with a parametric amplifier coupled to vacuum reservoir, in which the noise of the vacuum reservoir completely neglected or considered. Apart from the quantum and statistical property of dangerous reliable lasers, with a parametric amplifier driven by coherent light coupled to squeezed vacuum reservoir, all attention has been paid to the calculation of the squeezing and the statistical properties of these dangerous reliable lasers, and also the effect of the vacuum reservoir noise on photostatics and quadrature squeezing of the cavity light. The main objective of this research will be to investigate the quantum and statistical properties of degenerate reliable laser with parametric amplifier that are driven by coherent light. The specific objective, among the specific objectives, to calculate the photon statics, the mean, the variance, and the quadrature variance, quadrature squeezing of the cavity light, to study the effect of squeezing parameter and amplitude of the coupling coherent light on the quantum and statistical properties of these dangerous reliable lasers, and also to study the significance of the parametric amplifier and estimate the rate of the photon emission on the quantum and statistical property of degenerate reliable lasers. The significance of this study is to go from the squeezing production to application, as well as demonstrate the experiments and well understood of squeezing sources, and also useful to find some combinant means of generating a bright squeezed light. It's among the significance of this study. Operator dynamics, this is my models. So from this, this is the cavity mode, the light coupled between this cavity. So from this figure, we consider in which the degenerate reliable atoms in cascade configurations are available in the cavities, and we assume that we do know that this is the top level, this is the intermediate, and this is the bottom level of these three level atoms. And also we assume that the transition from the top to the bottom level and from the bottom to from the intermediate to the bottom level is dipole allowed, but the transition from the top to the bottom is dipole forbidden. And also we consider that we derive the strong coherent light from the outside to these three level atoms. This is the amplitude of driving coherent light, mu is the amplitude of driving coherent light. This driving coherent light couples the top and the bottom of these three level atoms, and also we consider that the case in which degenerate parametric amplifier can be put in the cavities. This is degenerate parametric amplifier. So we derive this degenerate parametric amplifier by the coherent light. This is the magnitude of the pumping coil of the light that drive the generator parametric amplifier. And also we assume that this cavity is coupled to the vacuum reservoir, and know that M node is the effect of the squeezing parameter incorporates M node and M node, coupled the cavity damping as the transmission loss. So by considering those, we have three interactions in the cavity. The first interaction, the driving coherent light couples the top and the bottom level of this degenerate cylinder with atoms. So there is interaction between this driving coherent light and degenerate cylinder with atoms. And again, we have the interaction between the cavity mode and this cylinder with atoms. And then again, we have the interaction between the cavity and degenerate amplifier. So by considering this interaction, we write the interaction Hamiltonians. The first represents the interaction of the driving current light that happens at the top and bottom level of the cylinder atoms. So we have the interaction of the current light with the degenerate cylinder with the atoms. And again, this is the interaction of the cavity mode with the degenerate parametric amplifier. This is the interaction of the cavity mode with cylinder atoms in the electric dipole approximation and the electric approximation. So we can write this interaction Hamiltonian by considering the other interactions. So then we can determine the master equations in squeezed vacuum reservoir by using these interactions Hamiltonians. Using this interaction Hamiltonian, we can write these master equations in squeezed vacuum reservoir. This is the master equation in squeezed vacuum reservoir. Then again, by using this interaction Hamiltonians, we can determine the quantum length equation for the cavity mode operators of the net. So this is the quantum length equations. So this length equations tell the time relation of the relation operators. Again, using the interaction Hamiltonians, and the equation of motion, we determine the equation of the relation of the expectation value of atomic operators by using the interaction Hamiltonians and the equation of motion. We can determine the equation of the expectation value of atomic operators. Then by applying the Lagrange approximation scale, on the quantum length equation, we couple the cavity mode and atomic operators. Then we can determine the steady state solution of those equations of the relation of atomic operators. So by using the steady state solution of the cavity mode and of the atomic operators, and also by using the quantum length equation.